So our question of the day is, why is it so crucial for us to understand how water functions, both physically and chemically, on our planet? So when we go and look at water, water really is going to break itself up or disassociate itself in a couple of different ways. So the way that we can write this reaction, the first one is that the hydrogen splits off, so we have a hydrogen ion and a hydroxide ion. Now, the hydrogen ion doesn't like living by itself. Water is slightly polarized, so what it tends to do is it creates that hydronium ion. So that hydrogen ion is going to bond with another water molecule and create this hydronium ion with the hydroxide. So, why do we say it this way even though it's not balanced? Well, when water does disassociate itself, it does so because of that slight charge the water molecules have. So the water molecules are going to attract each other. So the hydrogen ion on one molecule is literally pulled off and is physically attracted to another water molecule, and that's what creates that hydronium ion. So in this image we have this hydrogen ion slightly positively charged. That is going to be pulled off and it is going to be bonded then, and that's creating that hydronium. So it is slightly confusing, so we could write it like this. That makes it balanced, makes it easier to look at, makes it less confusing to some extent. However, it's not exactly what's happening in a solution. So it shows, regardless of how the dissociation is happening and what is happening, that the water molecule is disassociating. That's, in essence, the point that we're trying to get across, is that water is going to break apart. And it's going to create that hydrogen ion and the hydroxide ion. So, we have several names. We have the hydrogen ion, we have the proton, we have the acid. If we take that hydrogen ion and we slap it onto another water molecule, that creates the hydronium ion that we've been working with. So, since water is going to be pulling itself apart, what we can do is we can start talking about the equilibrium constant. Now this equilibrium constant, Kc, for the reaction is going to be the concentration of the reactants and the products, is what it's based on. So we're going to have the concentration of the products multiplied over the concentration of the reactants. So in this problem, water dissociation, only about 1 out of every 10 million water molecules is going to dissolve or disassociate. So our equilibrium, if we say, okay, I have 1, then we would set up our ratio for the hydrogen ions. The hydroxide ions, we're going to have the same number, 1 times 10 to the negative 7th of those. And so that's going to give us, so our equilibrium constant for water is 1 times 10 to the negative 14th. So what does that W mean on that equilibrium? So what that means is that this is so important in nature and in equilibrium that it is given its own subscript. So that means that, again, only 1 out of every 10 million water molecules is going to break apart. Water is very common on our planet, so this has its own known value. So most water is just that. Undisassociated, unbroken, whole, boring, ordinary water. The natural balance in a glass of water can be upset by dissolving substances into that glass. that either have a hydrogen ion or a hydroxide ion in them, that's going to increase the hydrogen ion or hydroxide ions to an amount that's more or less than that 1 times 10 to the negative 7th concentration. So these substances are known as acids and bases. So by definition, acids are ionic substances that have hydrogen ions acting as the metals. So hydrochloric acid, nitric acid. Bases are going to be our ionic substances that have the hydroxide acting as the nonmetal. This is our traditional definition. So sodium hydroxide, calcium hydroxide, so on and so forth. If we dissolve these substances in water, the question becomes, what's going to happen? What do we get? So if we take an acid like hydrochloric acid and we put it in water, it is going to dissociate or break apart. So it's going to separate. So this hydrogen ion, this hydroxide ion, that is representing that small amount that naturally dissociates in water. So that's that 1 out of every 10 million water molecules. So when we put something in there like hydrochloric acid, we upset the balance of the system. And there's no longer going to be an equal number of hydrogen ions and hydroxide ions. So now you may have more hydrogen ions or hydronium ions. And if we do, that means we have an acid. Now if I take a base like sodium hydroxide and I dissociate or break it apart, well, that's going to increase the amount of hydroxide ions that are naturally available in the water. So again, this is representing that small amount that naturally dissociates. So what's going to happen is our balance is going to be upset. There's not going to be an equal number of hydrogen ions and hydroxide ions. Now there's going to be more hydroxide ions. That means that we are going to have a base. So how do we determine? Do we have an acid? Do we have a base? Long story short, if our hydrogen concentration is higher than the hydroxide concentration, we're going to have an acid. Vice versa, we're going to have a base. Long story short. So there is going to be a scale, a metric. How strong is our acid? How strong is our base? And that is what we call the pH scale. So the pH scale goes from 0 to 14. 7 is what we call our pure water. So basically this is an easy way to determine whether we are dealing with an acid or whether we are dealing with a base. So anything with a pH of about 1 to 6, we could include 0 here as well, but anything less than 7, we are looking at an acid. Anything greater than 7, we are looking at a base. 7 is neutral, that's Switzerland. It's just boring water. So it can be slightly confusing because the greater the amount of the hydroxide ions, the smaller the pH value. So if we have a large number of hydroxide ions like gastric acid or stomach acid, it's going to have a very low pH. So let's talk about our scale here. So pH, by definition, is going to be a measure of the concentration of the hydrogen ion that is present in the solution. So we're going to find the pH by taking the negative log base 10 of the hydrogen ion concentration in molarity. So what do I mean by log base 10? So basically, when we are looking at our scientific notation and we have something that's 10 to the power of something, so 10 to the power of 7, log base 10 of that number is going to be that exponent, so it's going to be 7. By taking the negative of that, since our acid, we'll just use water as an example, we were looking at 10 to the negative 7th power. Negative of log base 10 of 10 to the negative 7th power is just going to give me 7. So if you look at your graphing calculators, you will see that you have two buttons on there. There's log and there's ln. We are going to be using log. That is programmed to be log base 10. So right now, if you take your graphing calculator and you type in log of 10 caret negative 7, you're going to get a negative 7 out. So that's why there's the negative in front of this formula. So our pH is defined as negative log base 10 of the concentration of the hydrogen ions in molarity. So how does that translate into our pH? So if we have a concentration that's 1 times 10 to the negative 2, we take the log base 10 of this number, we get a negative 2, we take the negative of that, and we get that the pH is 2. A pH of 2 tells us we are dealing with a very strong acid. That is lemon juice, vinegar, that kind of thing. It's extremely acidic. If we have a concentration of 1 times 10 to the negative 11th and we put it into the pH formula, we're going to get a pH value of 11. That is extremely basic. So that is a base. So here, if I'm looking for the pH of a glass of orange juice, I'm going to use the pH. Basically, it's asking what is the negative power of 10. So I put this in negative log base 10 of 1 times 10 to the negative 4th, and I get that the pH is 4. Now, this is only going to work if the number at the front is 1. Why? Well, user easiness. So, otherwise, we are going to have to definitely, absolutely put that in our graphing calculator. If it's anything other than a 1, right now, as most of you are still fairly new to logarithms, I would strongly recommend that you use a graphing calculator anyway, or at least a scientific calculator that has logarithmic functions on it. So if I have this 4.57 times 10 to the negative 2, what am I going to be doing? I'm going to be putting that in my calculator. I'm going to do negative log base 10 of 4.57, 10 to the negative 2, and what you get is a 1.34. So that tells me approximately, well, this tells me my pH value is about 1.3. Now, if I just want a quick gut check, I'm talking super quick gut check, and my number in front is less than 10, I can look at the absolute value of that exponent. That's a 2. That tells me I'm dealing with a strong acid. So, if I just need a quick gut check, acid or base, and the number in front is less than 10, I can just go straight to that exponent and look at the absolute value of it. So, conceptually, we are still looking at what is the power of 10, but just be aware, we are using this button, the log button. We are not using natural log. You will get to that, but not this class. So, if I have 100, and I say, okay, 10 to what power gives me 100? Well, that's 2, because 10 squared is 100. So, if I wanted to know what is log of 100, log of 100 is going to be what power do I raise 10 to in order to get 100? Well, that's 2. If I want to know what is log of 1,000, 1,000 is 10 cubed. So really when we're saying log base 10 of 1,000, we are saying what do I raise 10 to in order to give me exactly 1,000. And that is going to be, in this case, 3. Now, when we get to some unusual numbers, it may not be user-friendly. What do I raise 10 to in order to get 500? Well, that's not something I know off the top of my head. So I can do log of 500, and that tells me that 10 raised to the 2.69 is going to give me approximately 500. Now, I know it's going to be between 2 and 3 because 500 is between 100 and 1,000, but I don't know exactly how to dial it in any tighter without using technology. So, when we're talking a logarithmic scale, what this means is that every value means we are going up by a factor of 10. That is by definition. Back in the dark ages, before everybody had computers, we would often graph using logarithmic scales. It was a thing that we did in order to make our graphs fit onto the graph paper we were usually given in a lab. So, how do we figure out what we're dealing with? Well, step 1, we're going to be using our calculators pretty heavily for this. So log of 500, if I just type it in my calculator, I get 2.69. And so that's what I'm going to use. I've got 2.6989700, blah, blah, blah. And so I am going to be using this. Now, you want to make sure that you're using this button, the log button, not this button. This is log base E. E is Euler's number. And that is going to be 2.7182818, and so on and so forth. It is like pi, it is a number that never repeats. So our pH is always going to use the log base 10. So very often the common log does not have a 10 written below it. So this base is not written because it's considered a common log. It is used so frequently we don't even write it anymore. So anytime you see just log, it is an assumed log base 10. That is the mathematical and scientific definition of just log with no other base written there. So if I have acid rain and I have the concentration of hydrogen ions as 4.57 times 10 to the negative 2, and that's our molarity, then what I can do is I can go, okay, well that's going to be close to 2 for my pH value. I can put it in my calculator and get an exact value because that's not going to be exact because this is 4.57, not 1. So I'm going to put it in my pH calculation, and what I'm going to get is that this acid rain has a pH of 1.34. So it's close to 2, not exactly 2, but it's close to 2. That gives us an estimate to work with. It gives us something to ask ourselves, does our answer look like what we were expecting our answer to look like? So how does the amount of the hydrogen ion and the hydroxide ion change in the water when we upset the equilibrium? If we go back and we look at our example from earlier, if the hydrogen ion concentration is high, that means that there's been an acid that's added from pollution. So that would mean what we had some pollution added to our rainwater. That gives us the concentration, the molarity. Our hydroxide concentration would be lower. So we can calculate the pH of the solution, and we could even come in here and we could calculate the hydroxide concentration. for the solution. So to calculate our hydroxide concentration, what we're going to have to recognize is that the concentration of the hydrogen ion times the concentration of the hydroxide ion is going to equal 1 times 10 to the negative 14. That's a formula that allows us to calculate that hydroxide concentration. So why do we think the hydroxide concentration is going to be low? We have added a pollutant to the water, so we have added hydrogen ions. So let's go back and look at that concentration for water. So when we are looking at our concentration, we have this. So the fraction or the equilibrium is a natural balance in our universe. If the hydrogen ions go up, our hydroxide's going to come down. So water is going to always balance itself. So if we're adding excess hydrogen ions, then that is going to react with any naturally occurring hydroxides to reform water. So there's going to be a natural balance process. So that is going to decrease the amount of the hydroxides that we're going to see. So that is why this is always going to equal 1 times 10 to the negative 14. So when we go in reverse, that reverse reaction is going to occur when we dump in hydrogen ions. We are going to get lower hydroxide concentrations. If we dump in higher hydroxide concentrations, we are going to get lower hydrogen concentrations. So we're going to see this reaction working forwards and backwards. So our equation begins to look something like this up here. So why did the concentration become 1 on the bottom? Because if you remember from our earlier conversations before break, the concentrations of pure solids and pure liquids are not changing through the solution. They're going to remain constant. So in the equilibrium constant, we're going to write their concentration as 1, meaning it's not changing. Yes, the amount might change, but the concentration through the solution is not. So we are adding an acid. It's going to upset the natural equilibrium. So by adding an acid, maybe hydrochloric acid, something like that, we are adding some hydrogen ions. We are going to covet here. It's going to increase our hydrogen ion concentration, decrease our hydroxide ion concentration, because what's going to happen is these are going to start bonding back together with any hydroxides that are free roaming in order to get back to that equilibrium condition. So we frequently use pH. What is rarely used is pOH. So just as negative log of the concentration of hydrogen ions is referred to as the pH, negative log of the hydroxide ions is referred to as the pOH. Quite frankly, we use the pH instead of pOH when we're discussing how acidic or how basic a solution is. Mathematically, the term P means the negative logarithm of the number that follows. Is there any logical reason why we would want to actually use the pOH? Sometimes it can help us calculate the pH quicker. We don't have to do a little extra math. If we are given the OH concentration, we could crank that out pretty quickly. The important thing to realize is that the pH and the pOH should add to 14. Remember, our scale is 1 to 14. So what we're going to be dealing with is that if I look at the hydroxide concentration right here, 1 times 10 to the negative 12, I know my pOH is going to be 12. So that means my pH is 2. because pH and pOH need to add to 14. So sometimes it gives us a shortcut, sometimes it doesn't. The one we use the most, I would say greater than 95% of the time, is going to be pH. So just kind of a little bit. Now, our calculators, our graphing calculators, allow us to use decimals. There are some calculators that do not. So just be aware of that. You should not run into that on any of our calculators, but there are calculators that do run into that. So here is what we call the pH squared. This is in your note guide, and this is how the pH and the pOH are connected. So we are going to be moving on towards weak acids and weak bases and how they associate, dissociate in comparison with a strong acid or strong base. So just be aware we're going to be coming back and we're going to be looking at equilibrium constants again. So bring your questions.